Hello, everyone, and welcome to our webinar, Practical Applications for Extensional Viscosity. Today's webinar will be hosted by Dr. Christian Ochoa and Dr. Soha Shabani. Dr. Ochoa obtained his PhD in chemical engineering from the University of Illinois at Chicago, where he worked as a graduate researcher in soft matter and complex fluid research group. Dr. Shabani obtained her PhD in mechanical engineering from Iowa State University, where she worked on microrheology of hydrogels as functional materials. Today's webinar, we will be discussing the use of the Rheosense e-VROC technology to measure the extensional viscosity of polymer solutions commonly used in personal care products and bio-ink formulations. We'll be addressing the practical aspects of e-VROC measurements, as well as how the data can be used to predict performance. And without further ado, I will turn it over to you, Christian and Soha.
Thank you, Eden, for your nice introduction. Hi, everyone. Welcome into our webinar today. I'm Soha, and today I'm here with my colleague, Christian, and we're going to talk to you about practical applications for extensional viscosity and also give some quick background about our technology, and then we're going to share some extensional viscosity data that have been collected by e-VROC technology. So let's go ahead and get it started. I'm going to start off my presentation giving you some quick background about the importance of extensional viscosity in industrial applications. So you will learn about the practical aspects of extensional viscosity measurements, the nature of the experiments we have done, and you will understand why they are informative and important. Extensional or elongational viscosity is a fundamental parameter in many industrial processes. Here I'm going to show you some of these processes. For example, in plastic stretching process, such as blow molding, fiber spinning, and sheet extrusion, the plastic is constantly subjected to elongational deformation and is stretching or expanding in such processes. In common industrial processes, such as spray drying, jet breakup, drop formation, and filament stretching, and extensional deformation can influence the flow characteristics in these processes. So in order to design fluids with appropriate characteristics, which are commonly expressed as sprayability, spinability, printability, and jetability, you will be required to monitor and control the response of the fluid to both shear and extensional deformations. Polymers are among the most common materials used in industrial complex fluids and so contribute to the flow resistance in many extensional deformations that influence manufacturing processes such as inkjet printing, filament spinning, porous media flow, and enhanced oil recovery. Another situation where extensional viscosity is important is in food industry. For example, the viscosity of tomato ketchup is a major quality component for consumer acceptance. So it is necessary to control and adjust the processing parameters continuously to achieve a desirable and constant quality in the final product. So it is important to characterize the ketchup extensional viscosity together with the shear viscosity to have a complete say description of product flow behavior. And finally, if your work involves paints and coatings formulations or process development, then evaluation of extensional viscosity is critical for their effective application and performance. So these are some examples of industrial applications of extensional viscosity. And now I think it becomes clear why it is important to understand and measure extensional viscosity and how it can impact the industrial processes. With that in mind, in this webinar, we want to focus on two real-world processes where measuring extensional viscosity is critical: the container filling process and bioprinting applications. Actually, in our main webinar, we have had the full discussion on shear viscosity measurements of bioinks, data analysis, and we showed how we use our e-VROC technology to measure low and high viscosity bioinks over a wide range of shear rates. So if you are interested in this topic, you can download the webinar. Today, we are going to focus on another aspect that is extensional viscosity measurements. As I said, many real-world processes that involve complex fluids include an extensional deformation. If you have a fluid experiences an extensional deformation, a flow path with a change in cross-sectional area is a technique that you can use to get some information about extensional deformation. A common example would be a tapered flow nozzle that introduces an extensional component to the deformation of the fluid. Actually, this scenario is consistent with the container filling process used for personal care products like shampoo products, as well as various bioink 3D printing techniques such as extrusion-based and droplet-based bioprinting. Both processes I'm showing you here have a tapered flow nozzle. For formulation purposes, for example, it is important to measure the stringiness of a shampoo product. So we can somehow predict the stringiness by measuring extensional viscosity. Since materials used in these applications are typically non-Newtonian, we cannot predict extensional behavior from a steady shear viscosity, and so direct measurement is required. Today we will show you how we use our e-VROC technology to measure the extensional viscosity of polymer solutions commonly used in personal care products and bioink formulations, and we show how the data can be used to predict performance. So that was sort of the background on the practical and real-world applications of extensional viscosity, and now I'm going to talk to you a little bit about our technology that we use for measuring extensional viscosity. Our flow channel is a combination of microfluidic and MEMS technology. This schematic shows the dimensions of the channel, and this is an image of the channel. We have 4 pressure sensors that are located along the base of the channel, and they can measure pressure drop as the fluid flows through the channel. We have 2 sensors before the hyperbolic contraction expansion and 2 afterwards. This contraction expansion will change the velocity of the flow, introducing a velocity gradient in the direction of flow, which acts to stretch or elongate a fluid element. This is how the hyperbolic contraction expansion introduces an extensional component to the deformation of the fluid. The apparent extensional rate is the velocity gradient parallel to the direction of flow. We relate the apparent extensional rate to the flow rate and to the channel dimensions. We are going to talk about the normal stress difference in the next slide, but a parameter that is relevant to this is the Henke strain. To get a strain, we need to integrate the extensional rate with respect to time. We find that this strain is maximum at the middle of the constriction. Because the geometry is fixed, the Henke strain is dependent on these dimensions and is about 2. But because we still have the physical confines of the channel, we have no slip boundary condition at the boundaries. This introduces a shear contribution to the deformation as well. So this is not purely extensional flow. This is a mixed flow of shear and extensional. To calculate extensional viscosity, we need to get the pressure drop from the entry point to the exit point of the hyperbolic contraction expansion. So we measure the pressure drop between sensors 2 and 3, and then extrapolate the pressure drop to the entry and exit point of the hyperbolic contraction expansion. This pressure drop is delta PC. As you know, this is a mixed flow with pressure drop contributions from extensional as well as shear flows. Applying an extensional deformation generates a normal stress, analogous to a shear deformation generating a shear stress. If you have a Newtonian or power law fluid, you can use analytical expressions for the shear contribution to the pressure drop. But if you have something that doesn't classify as Newtonian or power law, we will have to use this delta PC uncorrected, knowing that it has contributions from both extensional and shear. The extensional viscosity is defined as this first normal stress difference divided by the apparent extensional rate. Okay, that was sort of review of our e-VROC technology, and now I'm gonna turn it over to my colleague Christian, and he's gonna go over some details of extensional fluid channel options and start sharing some data with you.
Thank you very much, Soha. So to design our experiments, we had multiple flow channels, or pretty much chip types that we could use for this. And we wanted to pick such that we had a wide extensional range to study. If you look at the dimensions here, the dimensions for all the extensional chip channels are fixed. And this is different from the uniform channels that have varying dimensions between A, B, C, and E chip types. So here are the different extensional tip types. And the letter in the middle there, that pretty much corresponds to the maximum pressure of each chip. So as you go from extensional chips A to B to C to E, your maximum pressure that you can access, that will increase. And this is pretty useful if you want to handle a broad range of extensional rates and also a broad range of viscosities. So to give an example, if you have a high viscosity sample, you can measure a broader range if using the C and E chips as opposed to the A and B. If you have a lower viscosity sample, you can measure a broader range with lower pressure chips A and B. So for our extensional rate sweep measurements, we used a combination of all these chips to get this broad range of extensional rates. So for the first set of experiments, we focused on polymer and surfactant formulations, especially those, and the reason for this is because these are used a lot for shampoo formulations. And determining the extensional viscosity for this is important to understand how these formulations are going to behave when they're dispensed from a bottle into your palm while you're washing your hair, and also how they will behave along tube constrictions and during the filling of containers in the industrial process. So if we look at the industrial filling process, some formulations can form strings of shampoo that can cause the shampoo to spill over the bottle cap. And this is a problem because the cap can then not be properly sealed. So even though you can try to fix this by slowing down the filling speed, of course, this will lead to a decrease in your throughput of your production line. So with our experiments with e-VROC tech, we want to identify the formulations that are more optical for these processes, and this will give you can give you the chance to get a higher throughput and save more in costs. So for our experiments, we conducted the first set of extensional viscosity measurements on high viscosity shampoo formulations at 25C. And we made these formulations by mixing these three ingredients shown here. So the first one is anionic negatively charged surfactant, SDS. So this is the cleaning agent. This serves to like clean oils, dirt, solubilize fat, and remove it. The second one is HPMC, hydroxypropylmethylcellulose. This is a biodegradable polymer derived from cellulose, and this is added to increase the viscosity of the product for enhanced storage stability, and also to obtain non-Newtonian behavior that customers desire in their, when washing their hair. So this polymer is also added to enhance and stabilize foam, and this is good with the customers because you get a nice lather when washing your hair. The third ingredient shown here is salt. So this is added to increase the viscosity and in such a way that not too much surfactant or other costly like surfactant SDS or other costly surfactant is used. So we made 4 formulations with different amounts of SDS and salt and 1 concentration of HPMC polymer. And we mixed the solutions at room temperature for at least a couple of days until the polymer was dissolved properly. And between all the measurements, we cleaned the chip flow channels with aqueous solution, which is compatible with these formulations. So this plot here is showing you the results, the extensional viscosity versus extensional rates. So these samples here have 28% polymer and 100 millimolar salt, and for 2 concentrations of surfactant SDS. So you can see that the samples decrease in extensional viscosity up to high extensional rates. You can also see that as the surfactant concentration increases, the extensional viscosity will increase. So now we're going to plot the samples that do not have any salt. So for the lower extensional rates, these samples have lower viscosity than the salt samples. And there's also a more gradual decrease in viscosity for these lower rates. Now, if you look beyond a certain rate, they actually show this apparent extensional thickening. And because of this, you get this crossover here. So pretty much the samples with salt have a higher viscosity at low rates and the lower viscosity at higher rates. So we have a couple reasons why adding the salt leads to these differences. The first one is that salt screens the electrostatic interactions. So this leads to decreased repulsion between the surfactant micelles in solution and unfolding of your polymer coils. And then this leads to the higher viscosity for lower extensional rates. The second reason is that salt promotes the formation of these worm-like, rod-like micelles. And it has been previously suggested that these micelles, worm-like micelles, align and slide over each other more easily under higher extensional rates. So this leads to lower viscosity at the higher extensional rates for the salt samples. So knowing what is plotted here, and if you want to have a lower extensional viscosity in your industrial filling process, we would prefer the samples with no salt for the low extensional rates. And then for the high extensional rates, you would prefer the samples with salt. So a couple more things about this data that are pretty interesting. You can see that there's extensional thickening for the samples with no salt, as I mentioned. So this may be influenced by secondary flows that are caused by elastic instabilities in the flow channel. Another thing is that if you look at the data in red, this extensional thickening here is likely due to turbulent flows in the flow channel. And this is why we have this dashed line here. So we calculated that turbulent flows in our flow channel are much more likely to occur if you fall to the right of this line. And to get accurate viscosity measurements, we don't want to have turbulent flows. we want to have the laminar flows. So moving on to the next slide. So the reason we want to have these laminar flows to get the accurate viscosity reading is that our viscosity calculations are based on assumptions of laminar flow. So to answer this question, as we probe this, we have the following question. When can we expect to get a transition from laminar flow to turbulent flow? So to start answering this, we define this dimensionless number called the Reynolds number. So this is a dimensionless group that comes out from when you non-dimensionalize the Navier-Stokes equation. And this corresponds to the ratio of the inertial to the viscous forces. So pretty much the inertial forces are the momentum of the fluid, while the viscous forces are related to the internal friction in your system. So this number can indicate for which conditions you might get a transition from laminar to turbulent flow. And this transition from laminar to turbulent occurs as the number increases. So if we look at if we were able to observe the laminar flow, all the streamlines would be parallel, such that you have this unidirectional flow. And then on the other hand, for turbulent flow, the streamlines would now cross, and you would get these interesting things like eddy currents, vortices, and the like. So for an extensional channel that we have, this is what the equation looks like. So you have density, the steady shear viscosity in the denominator here. U sub c is the characteristic velocity, and here we express that as the volumetric flow rate, and the channel dimensions that you can see in the schematic. Delta H is the hydraulic diameter, and this is expressed by the dimensions, and this value is pretty much one length scale that you can use that's appropriate for this geometry we have that has all these multiple length scales. So all of this allows us to calculate the Reynolds number with these values and dimensions. And for our extensional chip, the transition from the laminar to turbulent flow will correspond to Reynolds number of around order 10. So Reynolds number of around 10. So therefore, you're much more likely to get these turbulent or secondary flows above this Reynolds number. So now I will hand it back to my colleague Soha, who will go over the next set of experiments.
Thank you, Christian. So for the second set of our experiments, we examined extensional viscosity of bioinks. The goal that we had was to show how we use our e-VROC technology to measure extensional viscosity of bioinks over a broad range of shear rates, extensional rate. So we used multiple chips to test a broad range of extensional rates using just one instrument. We examined two groups of materials that are commonly used in bioprinting. We prepared 8% sodium alginate as a single component bioink. And in another interesting experiment, we blended 1% sodium alginate with 2% hyaluronic acid to develop a multi-material bioink that is expected to show more desired rheological and biological properties compared with a single component bioink. After this quick review of sample preparation, I'm going to go over the viscosity data I collected from our e-VROC and share some results with you. This figure shows the extensional viscosity as a function of extensional rate for 8% sodium alginate at varying temperatures of 25 and 37 degrees Celsius. So the temperature control system connected to e-VROC allows us to precisely control temperature and perform experiments at different temperatures. In general, as the temperature increases, the viscosity decreases, and for the bioprinting application, this is advantageous. Since the viscosity can change with temperature, it can be more compatible with 3D printing requirements. And in this sample, extensional thinning behavior is detected. That is a necessary property for the bioink printability in extrusion bioprinting. During a typical printing process, bioink is subjected to different extensional rates. So it would be beneficial if you characterize viscosity over a wide range of extensional rates, because the information that you obtain from viscosity measurements can help you for successful design and development of bioinks. For example, as seen here, the viscosity can be measured over a broad range of extensional rates from, say, 20 inverse second to about 14,000 inverse second. And the highest viscosity that was measured for this sample is about 140,000 millipascal second. That shows the capability of our e-VROC technology in measuring high viscous samples and over a wide range of extensional rates that are relevant to 3D printing process. With that in mind, now let's take a look at the viscosity of the mixture of 1% sodium alginate and 2% hyaluronic acid. This figure shows the extensional viscosity as a function of extensional rate at varying temperatures of 25 and 37 degrees Celsius. This is another high viscosity bioink that shows extensional thinning behavior. For the sample at 25 degrees Celsius, viscosity decreases from 40,000 millipascal second to about 2 millipascal second as the extensional rate increases from 20 to 10,000 inverse second. For 3D printing applications, you will need materials or bioinks that show good rheological and biological properties. So this is the reason that we mixed these two polymers. Basically, sodium alginate shows very good rheological properties, and it has good printability, but it cannot interact very well with cells, and it doesn't show very good biological properties. On the other hand, hyaluronic acid exhibit good biological properties and can improve biocompatibility of bioink. So the optimal formulation can be obtained by mixing these polymers, and we can develop multi-material bioinks that show improved rheological and biological properties. Now I turn it over again to my colleague Christian, and he's gonna go over the summary of our talk, and after that we can take your questions.
Thank you, Soha. So here we informed you of all the practical applications of extensional viscosity that we showed for these scenarios. So the applications focused on the filling process and the bioink 3D printing techniques. So it's important to understand the extensional viscosity if you want to optimize these kind of processes, including their formulations. And this is so that you can get a higher throughput, higher quality, and other parameters that you want to get. So we characterized, we did this by characterizing the extensional viscosity relevant to the processes. And for this, we used the e-VROC viscometer with multiple extensional chips. And we obtained the extensional viscosity versus the extensional rates for rates that span up to 3 orders of magnitude. So using the extensional VROC can help with understanding the flow behavior and extensional viscosity of many fluids that are used in industrial processes, especially fluids that contain polymers. All the solutions we presented today contain polymers. And if you wish to perform extensional experiments with the MVROC or even the Initium, you can feel free to contact us and we can help you with those. So that concludes our talk. Thank you very much for your time. And if you have any questions, we are ready to take those at this moment.
Thank you for a wonderful presentation, Christian and Soha. If anyone has any questions, please go ahead and drop them in the chat panel, and our speakers will be happy to answer those questions as they come through.
Actually, I see one question. Is the viscosity pure extension? Actually, with our technology, the viscosity is a combination of extensional and shear. So even with the hyperbolic geometry, we still have shear viscosity in our calculation. But as I explained, if you are dealing with Newtonian or power law fluid, you can correct your data. But if you are dealing with non-Newtonian fluid, actually we should use the delta PC uncorrected for measuring viscosity.
We have another question. When the channel change, is there any effect like die swelling? And then channel diameter or geometry change, for example. So we know that there can be die swelling that occurs for some solutions, but we haven't probed the circumstances if under which that occurs or not. We have another question is, can the e-VROC not measure extensional viscosity? Is it just the chip that allows us to do that?
Yeah, actually, our e-VROC technology, the difference between e-VROC and n-VROC is, I think it's just the chip type. So you can use extensional chips to measure extensional viscosity. So I think if you have n-VROC, if you just install e-VROC chip, actually extensional chip, you are able to measure extensional viscosity. And even our Initium also is able to measure extensional viscosity by using extensional chip.
So another question is, how would one correlate the geometry of your tech with, say, a slot die or application bar? So a way to correlate the measurements using this microfluidic geometry to, let's say, a similar geometry like a slot, a nozzle that has a tapered end. So it's might not exactly be the same as a slot die or application bar. So for that, you would have to, you can actually use equations to calculate the extensional rates that is experienced by your solution in the nozzle. And we found that relevant extensional rates in these industrial applications can range from about 30 to 300 inverse seconds. And this is well within the range that we can study with our e-VROC instruments. So another question is, can the shear component be calculated so that you have both shear and extensional data?
Yeah, actually the shear component can be calculated for only Newtonian or power law fluids. So yeah, if your fluid shows Newtonian behavior or power law behavior, then yes, the answer is yes, you can calculate the shear component. But if you are dealing with non-Newtonian fluid, the answer is no. So you cannot correct your data. So you just need to use the delta PC, and then your calculation involve both shear and extensional components.
So another question is, what limited the high pressure in the chip? So from what I understand is you're asking what would be the high pressure that can be probed by the chip. So that is limited by the full-scale pressure that that each of the A, B, C, or E chips that corresponds to each of those chips. So as you increase the chip letter type, the full-scale pressure will increase, and typically the values that you can probe correspond to about 5 to 95% of this full-scale pressure for each chip.
Can you please share the slides after the meeting? I think, yeah, I think that, yeah, we can share the slides, and also this webinar is recorded, so you can just request and we can share the recorded webinar with you. And so actually I just remember that for the question that asked about the extensional measurements on e-VROC, in addition to chip, you also need to update the software. So yeah, the software needs to be upgraded for extensional measurements. Then yeah, with a extensional chip and upgraded software, you can measure extensional viscosity. I just wanted to add this to my answer.
Okay, if there are no additional questions, then we can conclude the webinar here. Thank you very much for your time and your questions, for listening to us. And we wish you a great rest of the week. And thank you very much.
Thank you.